Well, hello, everybody. We're going to get started now. Um, I see we have a bunch of people connected. So welcome to lecture 13. This is the first lecture since um, the shelter in place order. So we're doing things a little bit differently. Obviously, I'm using Zoom, and I'm going to be recording with Zoom instead of having live recording as we had back in Corey Hall. But it should be pretty much the same as far as the recording. We'll record the lecture. It'll be mainly the slides, and then it'll be available online later. I hope you're all safe and managing the COVID-19 outbreak, and that you're in a safe and comfortable place. So with Zoom, I noticed nobody has their camera on except for me. My preference actually would be that you have your camera on, then I can see you, and it helps me to get some feedback, so I know you're understanding. You don't have to, but it might be nice to put your camera on. The other thing is, looks like some people are not muted, so if you're not going to speak, it's probably best to mute yourself. That way we'll have less noise. But of course, you're welcome to unmute yourself and interrupt me if you want, or raise your hand. If you want to ask a question, you can raise your hand with the app, and or you could send me a chat. Now watch for chats and watch for raised hands. And if you want to just speak out, you can do that. See what else did I want to say? Oh, about the exam. So you got the notice that we finished grading the exam. We'll give you a week for regrade requests. It looks like some people have already put in some regrade requests. The solutions will be posted. I think we're just kind of cleaning those up, so it should be posted pretty soon. The mean, as you saw, was 60 out of 90, which was somewhat lower than I expected. I think partly I may have made it too long. I don't know. I'm interested in hearing people's feedback on that, either now or later. I think, this is kind of new for me, a new experience, that this take-home exam thing. So I kind of figured it would be a little easier because you would be able to look stuff up. But if it was, too many problems, then you probably didn't have much time to look anything up. So sorry about that. I'll try to adjust moving forward. Like I said, it's a learning experience for me. I don't think I've given a take-home exam for many, many years. So let's see. I'm looking at some chats here. People are saying they thought it was too long. Yeah, it seems to be the unanimous decision. So, it will be, of course, the grade is curved, so you shouldn't worry too much about it. Okay, so we're going to get going with the lecture now, unless somebody wants to raise some other point. And to figure out how to do this now. Okay, so just bring up the lecture notes. Okay, so this is lecture 13, and this is all about power and energy. We'll touch on some of these topics later, but this is kind of the main lecture where we talk specifically about energy and power. So we're going to talk about energy and power in digital circuits. Before we do that, though, I want to talk a little bit about gasoline, because that's what we use to power our cars. And gasoline is a really good source of energy. It's very dense source of energy, actually, as it turns out. When we talk about energy, the unit of measure of energy is the joule, and turns out a gallon of gas holds about 130 million joules, which is really amazing. It's a very dense way to store energy. The energy is released when it's burnt in the engine, of course. And we're going to talk about power, and power is measured in watts. That's the rate of energy. So if you think of gasoline as kind of storing energy, and the gas pump kind of delivers it into the tank of the car, we could say that as the gasoline moves into the car, the gas pump is delivering about 6 megawatts. And by the way, 120 kilowatts, 1,000 watts, that's the power delivered by the Tesla supercharger. So the Tesla Model S has a 306 millijoule, not millijoule, million joule battery. That's good for 265 miles. So just kind of gives you an idea about how much is in a joule. But we're going to focus more on electronic circuits, of course. So just to recap a little bit, so energy is the ability to do work. Power is the rate of expending energy. So we say P is equal to dW over dt. And often we're going to talk about energy efficiency, and that's how much energy it takes to do some particular operation. Now, in handheld and portable devices that are battery operated, the main concern usually is with energy efficiency, because that limits the battery life. How much energy the battery can store will determine how many operations we can do on one charging of the battery. Right? So obviously, if we can make our circuits more energy efficient, we can do more operations on a given charge of the battery. Regarding power in handheld and portable devices, that's important because power is sort of the measure of how much energy is being dissipated per unit time. Most of that energy gets dissipated as heat. Right? So if we think about the power consumed by a device, that will tell us something about how hot it will get as it operates. And there's a limit to how much power we want to expend in a handheld or portable device, because it will get hot, or we have to find a way to dissipate that power. When we talk about infrastructure and servers, or computers that are plugged into the wall, we're less worried about power or about battery life. But we do worry about energy efficiency, because we have to pay for the power. I have to pay for the units of energy from the power company, and that's going to dictate the operation cost. Also, we have to remove the heat. And so the heat removal, air conditioning and fans and all that, contributes to the total cost of ownership, or the cost to run the data center. And at the bottom here, just a reminder, for electronic circuit, we can figure out what the power is by the product of the current times the voltage. So for a component, for instance, the current times the voltage is the power dissipated by that component. Okay, so what happens with computers? The sad fact is that computers turn electrical energy into heat. That's what they do primarily from a physical point of view, and computation is the byproduct of that, right? And so we make sure that the heat gets carried away either by air or water in the case of some servers or supercomputers. Otherwise, the chips will get hot and melt. Okay, so let's talk kind of back to the basics. If you look at a 1 ohm resistor as pictured here, and we connect a voltage source, say a DC voltage source across it, and that is a 1 volt power voltage source. You know from Ohm's law that this resistor, the current through here, will be 1 amp, right? So, and the power dissipated, because the 1 amp times 1 volt will be 1 watt, and that's 1 joule of heat energy per second. All the energy in this case is dissipated as heat in the resistor. So like I said, the watt, that's unit of power, that's the amount of energy burned in the resistor in 1 second. And the joule is the unit of energy. It also could be expressed as watt seconds, of course. So burning 1 watt for 100 seconds uses 100 watt seconds of energy. So just so you know, 1 joule of heat is the amount of heat that can heat 1 gram of water 0.24 degrees Celsius. Oops, seem to be stuck. I'm going to stop for a second. Oh boy. All right, go to the next slide and start sharing again. We'll see if this works. Okay, so here's an old example of a device. This is an iPod Nano. Some of you may remember this from years ago. Kind of like the resistor in the last slide, the iPod relies on passive transfer of heat from the case into the air. There's no fans or anything in this device, which is typical of handheld devices. And people don't really want fans in their pockets. So the general rule of thumb is for a device like this to stay cool to the touch or not uncomfortably warm through passive cooling, the power budget should be less than about 5 watts. So if this iPod Nano used 5 watts all the time, its particular battery would have lasted only about 15 minutes, right? So we can take a look inside and see. So this the battery is here, the silver thing. In this particular case, this is the 2005 edition. It had a 1.2 watt hour battery. So that means it could supply 1.2 watts of power for 1 hour, right? Which isn't very long. If it were expending 5 watts at maximum that it could be before it gets too warm, this battery, if you divide it out, this battery would last only 15 minutes. Right? So more watt hours would require a bigger battery, and that's a bigger form factor. It wouldn't be a nano anymore. It would be a large device. So, battery capacity is, as you'll see as we move through some more examples, has been one of the kind of limiting factors in devices and handheld devices and what they can do. The real specs for the Nano was it could play 15 hours of music or 4 hours of images, slideshows. So this works out to be that it was actually dissipating 85 milliwatts for music and 300 milliwatts for slides, for pictures. That's because the electronics in here were made to be pretty low power, right? So what's happened since then? In 2010, there was the Nano got smaller. This is not the iWatch. This is the Nano that could be mounted on a band like this. This one was 0.74 ounces, 50% of the weight of the Nano. This one had up to 24 hours of audio playback, which is a 70% improvement over the Nano. This one had a battery which is 0.39 watt hours. It's only 33% of the 2005 Nano. So there's a significant improvement in the energy efficiency of the circuits when going between these two generations. Right? That was because advances in IC processing and also some advances in the way that, or innovations in the way that the circuits were designed to make them be more energy efficient. And then in 2015, the Apple Watch came out, which you can see inside here. This actually had a bigger battery. This is a 0.78 watt hour lithium ion battery. It should provide up to 18 hours of use. So this was a big improvement, but I just wanted to show you what it looks like inside. You can see a lot of the area inside, or the volume inside, is occupied by the battery. And that's typical of portable and handheld devices. The batteries actually occupy a large amount of the volume, right? And sets a limit to kind of the form factor, how small these things can actually get. A kind of an extreme case of this is this, you remember the Google Glass, which was an interesting kind of product, not very successful for a variety of reasons, but pretty interesting kind of packaging. And if you look at, as you know, this was a pair of glasses that you could wear that had a little screen here that you look through, and so you could kind of overlay images on the real world. This is kind of the beginning of sort of an augmented reality type device. And in showing some detail here, you can see the battery is back here. There are speakers here. There's a camera looking forward here, prism display here, microphone here, Wi-Fi and Bluetooth radio here. Here it is in real life. The whole thing weighed 1.76 ounces. It's kind of about 4 times the weight of the iPod Shuffle, the smallest iPod. It had a pretty, here's the display. Here it was a liquid crystal on silicon prism projector. And then here's the battery back here. It was a 2.1 watt hour battery, which is about 5.3 times as much energy as the 2010 Nano. So it's a pretty big battery, and there's this big hunk of the Google Glass just dedicated to holding the battery there. And the logic board was in here. So it was a pretty nice kind of product design. This is what real phones look like. You may have seen inside your phone. It's mainly battery. There's a big battery in here, of course, because there's a lot of processing that happens in phones, not just for the software, but also energy is consumed for the radios for connecting to the cell towers or for Wi-Fi. This was, here's the iPhone 6. Now with iPhones, it's kind of interesting. They usually specify the battery capacity in terms of amp hours. So this is how many amps times hours. So in order to get it to watt hours, you have to know what voltage it's running at. In this case, it's running at 3.8 volts. So that translates to about 6.8 watt hour batteries. So here's just some more details if you want. I'm not going to talk about this, but you can look at these in the notes. These talks about all the different chips that are inside the iPhone 6. So the other big kind of line of portable devices are notebook computers or laptops. We used to call them notebooks because they kind of looked like notebooks. This is kind of the state of the art in 2006. The idea with these computers was they needed to be close enough to desktop performance. This was to get people to move away from desktops and start buying notebooks or laptops. By even 2006, not many people use desktops anymore. Here's the size. You've probably seen some of these old ones around. Ideally, they're kind of the size of a paper notebook, like I said. As far as heat, though, they could actually get a little hotter because it's rare that people hold laptops on their laps. Even though they're called laptops, you may have tried it and you notice that they get pretty warm. So can't get too hot on the bottom, but to keep them from getting too warm, most of them have fans these days. So if the processor gets too warm, then something in some circuit will turn the fan on to kind of cool things down. This is what batteries used to look like for these things. This is back when we had removable batteries, and they were pretty big, almost a full inch in depth. This one had a 55 watt hour battery, so that's meant for a 2.3 gigahertz Intel Core Dual CPU, which was the processor of the day. It would consume 31 watts running heavy load. So which meant under 2 hours of battery life, just for the CPU. But then there's other pieces to the laptop, like the display and the Wi-Fi radio and all that kind of stuff. Oops, am I stuck again? I'm stuck again. Hang on. There's some funny interaction between Zoom and Keynote. Okay. So, however, if the processor speed was lowered to 1 gigahertz, CPU would consume significantly less, only 13 watts. So this was kind of an energy saving mode that's often used, and most modern processors have this, where they'll run at different speeds, as we'll see later, depending on what the load is, in order to save battery life. So this was 46 times more energy than the iPod Nano battery. Right? So then there was kind of a change when Apple introduced the MacBook Air, because this was meant to be very compact. As you can see, it's very thin. And the way they did this was to get rid of the removable battery and kind of build the battery in the same way that iPods and iPhones are designed. So it was really, the idea was design a laptop more like an iPod. So the batteries were not removable and they're built right in. So if you're ever taking one apart, this is what you'll see. Um, and the batteries kind of spread out here, and you can see most of the volume of the thing is just batteries again. And the main board here, where it has the processor and other things, is only about 25% of the laptop. This this is the MacBook Air. It has 35 watt hour battery, which is only 63% of the 2006 MacBook, which had 55 watt hour battery. So again, there were advances in processing, partly due to Moore's law, to allow the processors to be more energy efficient, so that a laptop could manage with a smaller battery and still last a whole day or 8 hours or whatever the target was. Here's some more insides. I won't talk about this. So just to kind of remind you, there's 55 watt hours is about 180,000 joules. That's a lot of energy. And you've seen these pictures of laptops exploding when the lithium ion batteries somehow explode. It's not very common, but when they happen, you can see there's quite a bit of energy stored here. Okay, last thing I want to talk about before I switch into really talking about CMOS is about servers. So if you look at warehouse scaled computers, one of the things we think about there is the total cost of ownership, and that includes the price of the cost of buying equipment and then the cost of running equipment. And one of the expensive things is one of the expenses is removing heat, because in order to efficiently or effectively remove heat from these processors or servers, they have to be spaced out. So the ability to remove heat kind of determines how many servers can be put in a machine room. Stuck again. And then there's the electric bills. They add up. So not only do you have to pay for power for the processors, but you also have to pay for power for the air conditionings. So air conditioner, and that's a big part of the total cost of ownership. And then the third thing about power, why we're concerned about power consumption in servers, is that there's an issue of reliability. Running computers hot makes them fail more often. It's kind of the nature of CMOS and most semiconductor circuits is in accelerated heat, they tend to fail at a higher frequency or at a higher rate. So it's computers are much more reliable if they run at a cooler temperature. Okay, so okay, and then just kind of another kind of Moore's law type thing, but this is looking at energy efficiency. You can see the y-axis here is computations per kilowatt hour. So it's really operations per joule is another way to look at that, or energy per operation. And this is a logarithmic scale on the y-axis, and then time on the x-axis. And as most things like this, you can see that it's kind of an exponential improvement in energy efficiency over time, right? And you can see the computations per watt hour doubles every 1.6 years going back to the first computer. So that's pretty impressive. And again, this is largely due to Moore's law, and also due to some of the power or energy efficiency design methods that we will be talking about in a little while. Okay, so I'm going to transition now to talking about CMOS. So anybody want to ask anything or say anything at this point? Okay. Oops, I lost my slides. Huh. That's funny. Okay, so here we go. So CMOS circuits. So the basic idea with there's a few different ways that energy gets dissipated in CMOS circuits. Okay, the first one has to do with switching energy. Okay, and this is the energy required to change the voltage on nodes. So if you think of a logic gate changing its output, right, we're switching that node from a 0 to a 1 or from a 1 to 0. Every one of these logic transitions dissipates energy. And here's again, we will look at the inverter to kind of see prototypical example of what happens, but this could be any logic gate, actually. Any connection of transistors that changes a node kind of behaves this way. So when we switch a node from 0 to 1, right, what's happening there is the p-type transistor is charging up this capacitance, whatever that capacitance is. It's the internal capacitance plus the load capacitance, right? So during that process, current is kind of flowing through the p-type, depositing charge, which is accumulating here on the capacitance, and the voltage rises until it gets to VDD, and then the voltage across that transistor is 0 and the current stops flowing. During that process, as we've seen, the kind of voltage ramps up like that, and kind of a linear thing at first and then an exponential thing. There's the switching energy is 1/2 CV squared, C VDD squared. Okay, this is because what happens is there's a certain amount of energy that's required to switch that node. Half of it gets dissipated in that the resistance of that transistor, and half of it gets deposited here in the capacitance. And then later, if we take that node from 1 down to 0, we get this transition here. And again, we dissipate 1/2 CV squared. That's the energy there gets dissipated and turned into heat, really, across that the resistance of that N-type transistor. Okay, so this is kind of a fundamental thing. It's really independent of the technology. Whenever switching the voltage on a node, the energy associated with that switching event is 1/2 CV squared, which C is the total capacitance that's being switched. And V is in VDD, it's the voltage swing here in this case. So that's the fundamental thing for switching energy in CMOS, and that's a large component of the energy. In fact, it's most of the energy in CMOS circuits go into switching energy. So what could we do if we wanted to save energy? Of course, as designers, we would like to have our circuits be as energy efficient as possible, right? So what can we do? Well, we could reduce the number of clock transitions, of course, because every time this node switches, if it's switching according to some change on the clock, think of it this way: when the clock comes, the outputs of the state registers or the registers of flip-flop changes, and those changes propagate through the kind of cascades of logic gates, switching the nodes along the way, right? So if we could reduce the number of clock transitions, we could reduce the amount of switching that would have to happen, right? But we have work to do, so we have to keep the clock going. We could reduce VDD, and that looks like a good idea. But of course, as we'll see, reducing VDD limits the clock speed because the logic gates and everything slows down when VDD goes down. But we'll talk more about that in a little bit. Or we could use fewer circuits. Fewer circuits mean there's fewer nodes to be switched, right? But more transistors can do more work. We'll see later there's a way to trade off. When we talk about trading complexity for performance, making a more complicated circuit that has higher performance, that more complicated circuit also has more nodes in it, so it's going to consume more power. So usually cost and, or it's going to consume more energy per operation. So if we make an adder that has many logic gates into it compared to a simple ripple adder, the one with many logic gates in it, if it's doing its work at its job at the same rate as a ripple adder, it's going to consume more energy because there's more nodes to switch. So often we'll see that energy efficiency and complexity go hand in hand. And then the last thing we could think about doing is reducing the capacitance per node. And there's ways to do that, but this is also one reason why we scale the process, because when we scale the process, the capacitance is scaled down and takes less energy to switch. Okay, so if we look at this, take this dynamic power energy and look at it at the chip level and look at it over time, we can talk about the power due to switching, right, which is the energy per unit time for the entire chip. So we're going to have our 1/2 CV squared again, but I put alpha in here because now we're talking about the entire chip. We can talk about C as the total chip capacitance be switched. So that's the total capacitance of all the nodes on the chip that may need to switch. But of course, they're not all switching on every clock cycle. So we have a alpha here, which is the activity factor. It's kind of the average percentage of the capacitance switching per cycle, the number of nodes that switch. If you're really going to do a careful analysis, you could try to figure out what alpha is for a given circuit by using simulation. You can watch the activity on all the nodes and then kind of calculate this average, which would say on average how many nodes switch. And then this is VDD squared again. And then we have clock frequency in here now because we're looking at power instead of energy. This part is energy, and we multiply times frequency, which is kind of 1 over time. It's like energy per unit time, and that's why it's power. Okay, so that's kind of an important thing to remember because it kind of gives us a handle on what we can do to control the switching energy. There's another switching energy and switching power. There's another source of CMOS power, which is the so-called short circuit current. So it's interesting if you look at the dynamics of an inverter or a logic gate, as the input is changing, there's a overlap period. There's a period here when the input is above ground and below VDD, when both the P-type transistor and the N-type transistor are on a little bit. Right? So there's a conductance overlap. And so there'll be a little shot of current that kind of shoots down through when both of them are on. It's kind of like a short circuit between VDD and ground. And it's a very brief period of time, but you get these little current spikes here. It's worse, if you think about it, when you can see why if the input is ramping at a very slow rate, then this pulse will be wider because there's more time when both are conducting. Right? So that's another thing we think about. It's kind of hard to analyze exactly how much short circuit current there will be. It has a lot to do with the technology and the transistor thresholds and the layout and the sizing of the transistors. But it's important to realize that this does happen. There's another factor which is probably more significant, and that's the leakage currents. So even when a logic gate isn't switching, it burns power. And this kind of goes back to what we were talking about earlier a few weeks ago when we were talking about CMOS devices, is that if we had this inverter here, let's say, and the input was at 0 volts, so this N-type we expect to be off and the P-type expect to be on. So it'll be on and it'll charge up this output node, and this output node will be at 1 volt, right? But this N-type transistor isn't really completely off, as we mentioned earlier. So there's going to be some current that actually flows. This is the so-called sub-threshold current, which will flow from this node down. And that depletes some charge on the capacitor, which is replenished by a little bit of trickle current that comes out of the P. So effectively, I have a current that goes straight down from VDD to ground. So even when this transistor, the NFET, is off, it passes an off leakage current. And as we mentioned earlier, we can engineer, and I'll show you this again in a minute, we can engineer any I off we like, but a lower I off also results in a lower I on, and thus a lower maximum clock speed. So again, there's this kind of trade-off between speed and leakage current. And by the way, there's also a current that leaks through the gate of this transistor. Ideally, there'd be zero current here, but modern transistors have very thin oxide layer here, and they tend to have some kind of tunneling or other mechanisms so that a current will flow here. Again, that one's very small. This one is more significant. This has been a big problem in recent decades. Going back to this was some information from Intel in 2006. Back then, it was typical that half of the power of a CMOS chip was in leakage and half was in dynamic. Okay, things have gotten better since then, as I'll show you in a minute. But this is kind of a reminder when we looked at this was the idea, it's the current through drain to source of a transistor as a function of the voltage on the gate. And this was the threshold voltage here. So we can see the transistor turning on as we ramp up the input voltage. If we looked at this on the log plot, we saw that, so this is the maximum current here. And there was some I off current down here, which is very small. But if you look at it on a log plot, you can see that there's actually a Y intercept here. So there's a small off current, and here's the on current. So as I said before, by the way we dope during the processing, we can move this curve left or right. Right? If we move it right, it's going to lower the I off, but it also lowers the I on, and vice versa if we go the other way. Okay, so this means oftentimes processes, or in the past, processes have been kind of customized for different types of applications. So for CPUs and servers, for instance, we want high performance and we're a little less concerned about leakage current or the total power due to leakage. So it could use a process that had a low threshold, so you get high performance transistors because they'd have high on current, right? But also consequently would have a higher leakage. But if it's plugged into the wall, it's less of an issue, as opposed to, say, a cell phone or some kind of portable device where we need ultra low power and we're willing to give up a little bit on performance in order to get less leakage. Because a cell phone and devices like that spend a lot of time just powered on, not doing much processing. Right? So it seems like it would be a good idea to limit the leakage in that case. Okay. These days, our processes kind of mix the best of both of these, as we'll see later. And then there was kind of a significant improvement when the FinFET was invented. And this is a really nice picture of a FinFET device. You can see the cartoon over here on the left, but the background here is a photograph from a scanning electron microscope that shows a cross-section of the fin with the gate wrapped around it, and you can see the individual atoms in this fin. And this was a 22 nanometer process, and now they're down to 7 nanometers. So you can see there's not many atoms left in building and scaling down these devices. The significant thing, though, was that if you look at this curve that shows us the source of the drain to source current, this was a traditional planar device here in the black, and in the blue you see what happened with the Tri-Gate or the FinFET. It actually has a higher slope here, so it has a lower intercept, and so a much smaller off current. So one of the advances of FinFETs was that it decreased the amount of leakage current, so we can get high performance and low leakage at the same time. Okay, so this is kind of a summary of the total power that a chip or some particular circuit would be, total power that it dissipates. There's 3 components: there's the switching power, the short circuit power, and the leakage power. So, all right, so that's kind of the end of the basics on how how power is dissipated in CMOS devices. So in the remaining time, I'm going to talk about some techniques that we employ for low power design, right? Or what we can do as a designer to help control the power consumption or energy efficiency. Anybody want to ask anything? Okay. All right. So I'm going to go back to, I think yes. I have to stop that. And then, okay. So there's 5 design techniques I'm going to talk about. These are the primary ones that I know about. The first one's probably the most, well, the first one is probably the most important, and that's quite common. So I'll spend more time on that. So this has to do with trading hardware for power. Okay, and the way meaning we can actually use more hardware to make circuits more energy efficient. And it's kind of a very powerful and interesting idea. And when I say using more hardware, I mean we can use parallelism and pipelining for this. Okay, so the first thing is, I'm not going to go into a lot of details on this, but it turns out the gate delay is roughly linear with VDD. Okay, which means if we increase VDD, we get kind of a linear improvement in the delay of logic gates. So that's the first step. Now, if we had some kind of circuit as shown here, this is some logic block and has some VDD. And let's say what this is a logic block that processes stereo audio. So it'll alternate between the left and the right channel, right? So maybe use half the clocks for the left and half the clocks for the right. And to make things simple, we're going to just kind of assume kind of a unitless discussion here. Let's say it has a frequency of 1 and a VDD of 1 and a throughput of 1, meaning it does 1 operation per clock period. So we'd say that the power is proportional. We know power is proportional to frequency times voltage squared, right? Because we looked at that formula before. It was 1/2 CV squared F for the power. But we're just looking at proportionalities here, not worrying about the other things that are constant. So the power, according to, if all these were 1, we get the power would be 1, 2. Okay, and let's say it takes a unit area. So the power density is 1. Okay, so that's our starting point. Now, we could, it's not advancing. Sorry, I'm stuck again. Okay, I think this will work. Yeah, okay. So what we could do is we have really 2 streams of operations we're doing in this logic block if we're processing the stereo audio. So instead of using this one block to process both the left and the right, we can use 2 blocks. We use 1 block to process the left and 1 block to process the right. So we're using parallelism here. We're going to put 2 blocks in parallel and they're both working at the same time. We can do this because the left side processing is independent of the right side processing. They don't really depend on one another, so we can just separate them out into 2 different streams. So if we do that, let's say we set VDD equal to VDD over 1/2. So we scale down VDD by a factor of 2. And let's say we also scale down the frequency by a factor of 2 because we can, since each block is doing half of the work that this original block was doing, we can run it at half the speed, right? And let's say we lower VDD, and we'll see what that does in a minute. The throughput is still going to be 1 because if you look at the sum of these 2, right, I think I have it here, yeah. but because the sum of the two, each is doing half the work, the total is still throughput 1. The power, though, is interesting. We're going to have the total power is going to be 2, because there are 2 blocks, times the new F, which is frequency is 1/2, and the new voltage squared, voltage is VDD over 2, so it's 1/4, right? Before it was 1, now it's 0.5 squared, so it's 1/4. So if you multiply this out, you get the power is 1/4 of what it was before. So by splitting these operations into 2 blocks and running each block at half the speed and half the voltage, we get the power down to 1/4 of what it was before. Right? So the energy efficiency of the energy per operation is much improved. Right? So that's a really kind of powerful idea. Keep in mind, so we can do this in general any way we can find parallelism. We can, if we can parallelize a problem and use more hardware, we can use more hardware so that each block is doing each less work, right? Lower the frequency on those blocks, and also lower the VDD as well. See, the reason this, and we rely on this kind of linear dependence on VDD. By lowering VDD by 1/2, we only need to lower the frequency by 1/2, right? That's the trick. This assumption about linearity, which isn't exactly right, but it's pretty close, right? So we lower VDD by 1/2. That will slow things down, will cause us to slow things down by 1/2, right? But because VDD is squared in the power formula, we get a square advantage, okay? So this technique was actually invented here at Berkeley back in the 90s by these guys, Broderson, who's a retired professor here, and his student, Anantha, who now is at MIT as faculty. He was department chair for EECS, and I think he's the dean now. And they prototyped a lot of this in one of my classes, my circuit design class. So they wrote a paper where they studied different ways of parallelizing, or taking basic signal processing operations and making kind of comparing a simple implementation to a parallel implementation and to a pipeline, and some combined parallel and pipeline. And the results are here in the table. Of course, the area gets bigger when you do this, right? So if area is a limitation, it may not be your best technique. However, you can get parallelism by pipelining, in which case it doesn't take much more area. So you can see the kind of parallel pipelined version. Here's the voltage, and you can see the parallel pipeline version here. The power was only 20% of the simple version, right? So there's a big benefit here. Another example of this was this chip designed by Intel. Kind of just demonstrates the point again. This was a graphics vertex pixel shader in 32 nanometer CMOS. And there's a lot of, as you can imagine, in graphical operations for shading and operating on pixels, there's lots of parallelism that's available. So you can run things in parallel to get high throughput, and then lower the throughput, higher throughput than's needed, and then lower the throughput by lowering VDD, and thus lowering the clock frequency and getting better energy efficiency. So you can see here, this is some results from the chip. The red curve here is the total power. The blue is the performance in million vertices per second. This is kind of the throughput, number of operations per second. And you can see in the high performance mode up here, it's at 151 milliwatts, and it gets about 2 billion vertices per second. If we go down here to the, and that's the power there, 151 milliwatts. We can lower if we lower the supply voltage from here, it was about a little over 1 volt down to I don't know, 0.55 volts, so about half the voltage, the power goes down dramatically from 151 milliwatts down to 3.4 milliwatts. But the performance, the throughput's not hurt that much. Actually, you get 190 million vertices per second versus 2 gigs. So it's about a less than 10% decrease in performance, but a huge factor in power. Okay, so the same idea is why, to a large extent, that most processors these days have multiple cores, right? Because multiple cores give us a way to achieve the same amount of processing with more energy efficiency. So rather than running a single core at a very high frequency, you can run multiple cores at lower frequencies and lower voltages, right? And therefore get more energy efficiency. And this is possible as long as there's a way to parallelize the work that needs to be done. Right? And typically you can find operating systems can find multiple different processes that need to run at the same time and issue those on different cores. So the first time this was done in practice was a chip that was designed by IBM along with Sony for the PlayStation 3. You can see a picture of the chip here. You can see there's a lot of repeated things here, and those repeated things are these processing units they called SPUs, or synergetic processing units. So they had a Power PC, which is a kind of a RISC type processor here, and then an array 8 of these SPUs, and they all ran in parallel. And the Power PC would farm out work to these SPUs. And the reason I show this chip is that we have this so-called shmoo plot for this chip. A shmoo plot is shown here. What it is it shows the regions of operation for a device, like a processor like this. And you can see as we vary the frequency from 2 gigahertz up to 5 something gigahertz, and then vary the voltage. Right? We fill in this table and we show when the chip is functional and when it failed. So if the frequency goes too high for too low of a voltage, then it won't operate correctly because there'll be too much gate delay, right? And there'll be errors. This region is where it functions correctly. And in each box, we show what the temperature was, which kind of tells us something about how much heat is being dissipated and how much power is being dissipated. Right, so this is typically done when a new product is, or a new chip is being developed. After it's manufactured, it'll get tested and we'll fill in a table like this so you can see that if it's operating according to specification. But we can find some interesting things here. So here in this, if you look in one column here, you can see if we lower VDD, right, according to these formulas here, we know that there'll be less dynamic switching energy, right? We can see that because the power consumption went down from 7 watts to 2 watts for a given clock frequency. And as I mentioned, if we lower VDD too much for a given clock frequency, it'll stop working. But you should remember that changing the clock frequency alone doesn't really help the energy per operation. Because the energy per operation is really this, it's 1/2 CV squared. There's no F in here. The power formula has an F. So if we change the clock frequency without changing the voltage, as you can see here, it actually changes the power, but the total energy is the same. All this really does is it takes a certain particular computation. By lowering the clock frequency, it just spreads it out over time, but it's the same amount of switching. It's the same number of switching events. It just happens over a longer period of time. So on per unit time, the energy being dissipated is less, but the total energy doesn't change, right? If we really want to make the energy per op better, we have to change not just the clock frequency, but also the voltage, right? So that's, I can show that here. So here at 7 watts, we need 7 watts to get reliable operation at 4.4 gigahertz. Now, it take 1 watt to get 2.2 gigahertz performance down here, right? So what does this mean? We went from 4 gigahertz down to 2 gigahertz, and we changed the voltage down here to 0.9 from 1.2. It's not a big change in voltage, but you can see that the power went down from 7 watts to 1 watt, right? Even though the voltage only changed from 1.2 to 0.9, and the frequency was only halved, right? So a lot of this is because VDD is squared in the power formula. So if a program needs 4.4 gigahertz of CPU, and it could be recoded, written as 2 independent threads or 2 independent programs, and could use 2.2 gigahertz CPUs, that's a big win, right? Is you're going to get the same effective performance, you're going to get 2.2 times 2. So you get the same performance as this point here, but you can do it with 2 watts instead of 7 watts. So that's the whole power of this technique. Okay, so that was kind of the first technique. So that's kind of an important one to understand. And it's used very commonly today. And it explains the move towards, the move that happened when we stopped making processors, single core processors go faster and faster and started using multi-core processors. Okay. The next technique has to do with powering down idle circuits. Right. So this is a technique where we can use some extra transistors that are in between the power rail, as we say, VDD, and the logic circuit, in between the logic circuit and ground. Right? And what these can do is these can put a block to sleep. For instance, if there's a floating point unit in a processor and there's no floating point operations that are being used, we could put that put that block to sleep. Okay, what it does then is obviously cause any nodes from being switched, and also prevents, if these transistors can turn off well, meaning they have a high logic threshold, then it could keep leakage current from occurring in this block as well. Right? So when there's asleep, the leakage current is power is dramatically reduced, and since there's no power in here, no nodes are switching. There's no dynamic power as well, right? So it doesn't come with a cost. The presence of the sleep transistor slows down the clock when the logic, or slows down the block actually when the logic block is in use, because the power then has to come through some resistance here, right? But it's an effective technique and it's used. Here's an example with some cache blocks. And you can see without the sleep transistors here, all these blocks. This is a thermal map that shows heat being dissipated, I believe, or it's a voltage contrast. I can't remember, one or the other, but it shows activity here. So the idea in this cache, it was designed with the sleep transistors on a per block basis. So if this particular piece of the cache is being accessed, then the controller would turn on the transistors, allow it to be powered, and then the block could be captured, or it could be accessed, and all the other blocks would stay asleep. Right? So this could reduce the leakage in active blocks by 3x. There's a kind of another example of this. This was a chip that Intel designed for cell phones. It never caught on very much, but was interesting. SoC has audio, had CPU, had graphics, has video, display, controller, image, a signal processor, a security engine. And this one was designed so that you can see in this picture here that the controller had control over powering up blocks that were needed or not needed. So the software could turn blocks on and off according to what was running at a particular time. So here's kind of shows, again, with thermal imaging, you can see which blocks are active and dissipating power. And this was what it looks like when playing a video game. You can see there's of course, red is more power and green is less and blue is even less. Yellow is kind of in between. You can see the graphics engine for a game and the video part is very active here. A little bit of the image signal processor and some for the CPU. Not much for the security engine. And then if you're watching a video on this device, the CPU is not doing much. It's mostly in the graphics and the video part, right? And this is just looking at the phone screen. Not much is going on. You can see everything is pretty much blue. It's a little bit happening here in the CPU. I think that's in the cache, right? And then when the phone's in your pocket, just kind of idle waiting for a call, there's just a little bit of power in the power management. Everything is kind of sleeping, waiting for some kind of signal or interrupt coming in to wake up the CPU. So it's in some kind of standby state. Okay, so that's that technique. So we can put power transistors to turn off, power off blocks that aren't being used. That was the second technique. The third technique has to do with slowing down the slack paths. I'll show you what I mean by that. So this is a picture that I showed earlier when we were, or a few weeks ago when we were talking about timing and critical paths. We said this was the critical path. This was the histograph that shows how many paths through the logic circuit have what amount of timing slack. And the timing slack is extra time, meaning the signals get to their destination, either flip-flops or registers or the output, early, and then just wait for the clock. Some of them get there late, because this one isn't quite completely finished being designed yet. The one that is the slowest path is the critical path. And all these have extra time. Those paths actually get there, they're too fast. So what we can do is take those fast paths and slow them down through one means or another. One way would be to use several voltages on a chip. We could have multiple supply voltages. So we could, the circuits that need to be fast because they're on the critical path, they could run from using a higher supply voltage, and the ones that can be slow because they're on the off critical path or they have extra timing slack, they can be slowed down by using a lower VDD, right? Which will, because it's a lower VDD and VDD is squared, they will consume less power. Right, so that's kind of a good idea, and this has been tried. It's awkward to have multiple supply voltages, and so a more common technique would be to use a process that has multiple transistor thresholds, meaning you can specify when a transistor is used what its threshold voltage is, and there might be multiple different threshold voltages. Okay, so on transistors for gates, that are off the critical path, we could use high threshold transistors. They're going to be slower because they're going to have less on current, but they'll have less off current. So we can save on leakage quite a bit by choosing those high VT transistors for the off critical paths. And then just the few critical paths, the few paths that have to be very fast, they can use low VT transistors. They will be more leaky, which means they'll dissipate more static power consumption, but they will be fast, so we can meet the high performance needed to meet the clock constraint. Right? So that's actually quite a common technique these days. And in fact, cell libraries for modern ASIC processes will have multiple different cells, like they'll have two different style NAND gates, for instance, one NAND gate that's designed with low threshold transistors and one that's designed with high threshold transistors. And the tools, since they understand the delay to your circuit, they will choose the proper cell in order to make this optimization. And this is just one of the first demonstrations of that. This was the ARM, low power ARM that was designed, where the logic was partitioned into 0.8 volt sections and 1 volt sections. It was done manually for this paper. And then, of course, signals had to flow between the two, and since they're at different voltages, they need some level shifting circuits to allow a signal to go from one voltage domain into the other. Right? But they demonstrated that this was possible, and that there was a 50% dynamic power cut in the 0.8 volt section, and the leakage in the 1 volt section was cut by 70% by using high VTs. So, okay, so that was the third technique. The fourth technique is shown here. Has to do with gating clocks. And let me motivate this. So if you look at a CPU and ask where most of the power goes, it's quite common that a lot of the power, as you can see here, goes into the latches. And it's not so much the latch circuit itself, it's the fact that the clock, that the latch, there's a lot of, when it says latches here, it actually means flip-flops and latches and registers. There's a lot of those on a high performance processor. And the clock has to connect to all those, and it has to switch all those connections to the flip-flops, the gate connections, and there's a lot of capacitance there. So a lot of power goes into, you can see here, not just distributing the clock, but also switching the clock nodes at the latches and flip-flops. Right. So, however, in designs, most of the time the latches don't change state. If there's a clock enable signal as an input to a latch or a flip-flop, and the clock enable signal is only true occasionally, right? Only when that flip-flop needs to change state, right? So what we can do is gate the clock. What this means is the clock signal is distributed through the whole chip, but locally, if it's connected to a set of flip-flops, let's say in a register, and that register has a clock enable, we can and that clock enable effectively with the clock and only let the clock switch the capacitance of the clock connections when the clock enable is true. Right? And the CAD tools will do this. So here's a picture that shows what the Synopsys design compiler can do. So if you had a configuration like this where this is a register, it says register bank, but it's a register, it's a bunch of flip-flops. And here's the clock is distributed, and of course it connects to all the clock connection on all the flip-flops. If you remember our circuits for that, that was in a typical scenario, this clock signal will connect to the transmission gates inside the latches. Right? There's lots of connections there. So there's lots of capacitance there on this node. And then the clock enable is effectively implemented this way. So if there's a clock enable signal, what it does when the signal is, when the clock enable is true, then this data input is allowed to go in and change the state of the register. When the clock enable is not true, or when it's a 0, we just recirculate the value back into the register. Right. So what we're doing here is, in this case, there's the capacitance that has to switch associated with those flip-flops there. And also we have to change the state of the, actually we won't, but this signal gets, no. So I guess, sorry, the energy is on switching the input to the registers there. Now, an alternative, oh, okay. Let's see if I can get to you.
Um, well,
Want to
Professor,
go ahead and ask you a question if you want.
yeah, actually, I do not catch on the meaning of.
Are you muted?
I think, no,
You want to
I
ask
have
a
not.
question?
Yeah, okay. Actually, I do
Okay.
not catch on
Well,
the meaning
maybe later.
about
Okay, so I'm going to go
get
back.
the cloud.
Hang on 1 second. Okay, back to this. All right, so what we can, as I said before, we effectively, and this is a little circuit that's in here to help prevent glitches, but the clock signal gets ANDed with the enable. It's really a latch version of the enable signal. And so this does two things. First of all, the only clock load then is the connections to this, even for this whole large register here, just connects to these 2 points here, so there's significantly less capacitance to be switched. And that's going to happen in every clock cycle. But then these internal nodes will only get switched when the clock enable is true. So only when it's time to actually change the state in the register do we need to switch those clock nodes there. Right. So this is another optimization that's done commonly. In this case, I showed it for Synopsys Design Compiler. That's the tool, one of the tools that we use for logic synthesis. So the logic synthesis tools will look for the situations where there's an enable signal connected to a common enable signal for a bunch of flip-flops, and then replace it by a gated version of the clock, which gets gated by the enable signal. Okay, so it's effectively like turning off the clock when the enable signal is low, and turning the clock on locally here when the enable signal is high. So that can save a significant amount of energy because there's a lot of energy expended in switching those clock connections to flip-flops. Okay, and then the last technique is thermal management. And it's kind of interesting if you look at the relationship between leakage current and voltage. I had the formula earlier in the slide, but I didn't talk about it. But it turns out that the leakage current is exponentially proportional to the temperature. So when we heat up a CMOS chip, it leaks more and more. This is kind of a bad thing, actually. I say here a recipe for thermal runaway. What I mean by that is, in principle, if you heat up the chip and it starts leaking more, this more leakage current is going to cause more heat, right? Because that heat gets dissipated in the transistors, right? And then more heat causes more current, leakage current, which causes more heat, et cetera, et cetera. So you could imagine that there might be thermal runaway if it gets hotter and starts leaking more, kind of in a positive feedback loop. But the point is that if you keep chips cool, they will leak less. So that's another way, by proper temperature control, right? And so for big CPUs that you see in servers, they'll typically have fans on them connected right on the CPU, and they'll blow air across to remove the heat. At least there will be a heat sink, which will be a metal structure with some fins sticking up in the air to help dissipate the heat. In some extreme situations, there's actually water cooling in some servers where there'll be water that's circulated by the chips and some heat exchanger that will pull the heat away. Water is a much better conductor of heat than air, so that's a much more efficient way to do it in situations where there's a lot of heat that needs to be dissipated. So this is why we work hard to keep servers cool, is to help minimize the leakage. This just is kind of a fun picture of IBM Power 4. This was an old IBM chip that was designed, and they had this nice package that had put 4 dies in a multi-chip module. The chip had 2 CPUs per die. This is kind of the technology they used in their mainframe computers. And this shows a thermograph of heat dissipation. And this chip was able to dissipate 115 watts, which is quite a bit. And you can see a lot of it here in the fixed point units in the cache. So most modern day processors these days monitor their own temperature. And if they're getting too warm, then they will slow down the clock speed to slow themselves down. And they usually do that by lowering the voltage as well. So they'll lower the voltage and the clock speed at the same time. And that'll make the chip dissipate less energy and also make it, or less power, and make it more energy efficient. So there's a kind of a complicated controller on most processors that will do that. Also, when the operating system can put it into a kind of a power savings mode when there's not much work to be done. And when it goes into power saving mode, as I mentioned, it will typically lower the supply voltage and lower the clock at the same time. And this will all help the chip dissipate less power and help keep it cool. So those were the techniques. So today what I talked about, started talking about, constraints about power consumption and energy and batteries and in modern devices. And we talked about the fundamentals of power dissipation and energy use in CMOS circuits and where it comes from. And then I presented 5 different low power design techniques that we can use for optimizing for power and power consumption and energy efficiency in CMOS circuits. And I think that's all I wanted to say. See, stop the share. If anybody has any questions, you can ask now.
Professor, can you hear me?
Okay, your hand is raised. So you want to ask a question? Go ahead.
Yeah, Professor.
I can't hear you. Yeah, are you muted?
No.
Oh, I'm sorry. I had my sound down. Go ahead.
Okay, it's okay. Actually, Professor, I did not catch on the meaning of the clock gating. Is that just means that we use a latch to control that whether this clock can be entered to the chip or?
Yeah, that's right. That was a combination of a latch and a AND gate. The most important part is the AND gate because we AND the enable signal with the clock. So effectively, if the enable signal is low, then the clock doesn't make it to the register.
Let's see. So
and the latch is in there to help. If you analyze this, there's some circumstance. If the enable signal comes too soon, then it's possible to generate a glitch. So the latch is supposed to prevent the glitch from happening.
I see. So the principle is quite easy. Quite simple. We just use latch to control the clock.
Latch and an AND gate.
And gate. Yeah, yes. This is
that's in those circumstances. Gating. Yes, where there's a clock enable, there's that technique can be used. Yep.
I see. Okay, thank you very much.
Okay. So it looks like we're just about out of time. Anybody else? Okay, well, thanks. And I hope you all stay well. I'll see you again on Thursday.
See you.
Okay, bye-bye.
Bye.
Bye-bye. Thank you.